All right, so I want to talk a little bit about the theory of the pressure effects. A couple of the earlier talks have alluded to this before. First of all, if you have a gas phase reaction and you change the pressure, it's pretty obvious that the concentrations change, right? So if you have like a sample of a gas in a piston and you squeeze it, the total number of moles stays the same, but you made the volume smaller. So therefore, the concentration increases. So if you have constant mole fractions, like you would if you just set them close to a piston, then you can calculate the concentrations from the mole fractions, and the concentrations would go up. And if the rate coefficient was a number, and you increase the concentration, then the first order reactions the rates would all go up first power. But these are the rates moles per centimeter cubed per second. But you've also made your volume smaller if you've compressed it. So if you multiply the rate times the volume, that's the total number of moles that's changing, say, in your piston. And that number will be unchanged by the compression. So the first order reactions, if it's isothermal compression, to first order, nothing changes with the first order reactions. And on the other hand, the bimolecular rates are dependent concentration squared, the concentration of A and B reacting with each other. So the R, moles per centimeter cubed per second, goes up as pressure squared, and the total moles will increase first power in the pressure. Okay, so that's like the obvious thing, and you knew about that from when you were in high school. All right. Something that a lot of people didn't learn in high school, but is a true thing, is that both K equilibrium and Kc are independent of pressure. So if a reaction is equilibrated, the concentration ratio, the concentrations of the products divided by concentrations of reactants, is unaffected by change in the pressure. However, if the reaction changes the number of moles of gas, if you wrote your equilibrium expression in terms of mole fractions, that would change with pressure, because the mole fractions are related to concentrations by a pressure. So if the concentration ratio stays the same, mole fraction ratio can't stay the same if you change the pressure if the number of say, products is bigger than reactants. And you'll have like pressure squared in the numerator and pressure in the denominator. So this is like a little subtle about what happens to equilibrated stuff as you change the pressure. And so just be super careful about this. And I've seen numerous mistakes with this, particularly when I taught thermo to the undergraduates. It's just like, I don't think a single student got it right. All right, and then if you have some sample of gas in your vessel and it's isothermal, and you just squirt in some more helium, the pressure definitely goes up, but all the concentrations don't change because you still have the same number of moles of everything in the same volume. And so to like 0th order, nothing happened by adding a bunch of helium. Okay? And it doesn't affect the equilibrium constants at all, having the extra helium there. So that's no effect. It changes the mole fractions because now I've added extra moles of helium, so they all change. But then you have the same kind of thing. In the concentration ratio of equilibrium would stay the same, but the mole fraction ratio would change maybe. But the subtle thing is that you might not know much about is that adding extra helium or increasing the pressure does change the rate coefficients. And so that's what I'm mostly going to talk about today. So it's just a thing to keep in mind is that rate coefficients depend on more than just what the reactants and the products are and the temperature. So everybody knows it depends on what the reactant, what the product is, what concentrations on them are, what the temperature is. But it also depends on the solvent. It also depends on an interface if you're doing a catalytic reaction. It can be affected by presence of photons and by electric fields. So far, RMG doesn't know anything about that. It definitely can depend on the pressure and weakly on the Beth-Geth composition. And that's what we're going to talk about today. All right, so it turns out that unimolecular reactions are very often pressure dependent in the gas phase. And the fundamental issue is that if you're going to take some molecule and make it vibrate so hard that it's actually going to break a bond or do some reaction, you need to put a ton of energy into it. So it takes lots of collisions with bath gas to absorb enough energy to get up to that high energy to react. And similarly, if I make some energized, I get over the reaction, I'm vibrating like crazy, I make some products, they might have a lot of energy because I had a lot of energy to get there, and it might take a lot of collisions to cool the thing back down too. And so the thermal relaxation or the heat up time might turn out to be longer than the chemical reaction time scale in gases if the pressure's low enough. So certainly in like interstellar space, you have a reaction, it makes a molecule. It's a heck of a long time before that molecule can have collisions with other stuff out in interstellar space in order to cool down. So this effect would be gigantic there. In a lot of the vacuum experiments, like in our lab next door, we do experiments at 10 torr. Again, the pressure's pretty low, and you can often get situations where it's like an excellent thermal insulator. You don't really have much exchange of energy with the gas. There's not much gas. As you get to 100 atmospheres, you get into liquid phase. It's a totally different situation where normally thermal relaxation is fast compared to the chemical reactions. And that's the normal case. The normal case is we assume everything's Boltzmann. We have a temperature. The temperature assumes you have fast thermal equilibrium. The collisions of the bath with your molecules are fast to keep everything at a uniform temperature. If you don't have that condition, then you get this weird situation. It's non-thermal, and you can have rates that are really strange, which I'm going to show you about. And so this is going to be a big headache for us because in our simulation models, in RMG and in ChemCin and in Cantera, we always write rates as a function of temperature. The implication is we know what the heck the temperature means. But if you have some molecules that are not at thermal equilibrium with the bath gas around them, well, the bath gas temperature, maybe that's a real number, but what the heck is the temperature of the molecule? Okay, and so this whole thing is actually, we know the molecules are not really at thermal equilibrium, but we're going to kind of pretend or re-express everything in terms of the temperature of the bath gas surrounding them. All right, so at high pressures, this is the normal case you're used to. You say, well, A and B react, they form some energized C because it's an exothermic reaction, but there's a lot of bath gas around, you have very fast collision, so C very quickly becomes thermalized, hence the Boltzmann distribution. And that's our normal case. A plus B reacts to make C. And after a while, you make a lot of C, and then you could have C react over to D, and then later maybe D might react to make E plus F. And so we write this down, and this is like the simple way that RMG would work, where it writes down sequential reaction steps. First step, second step, third step. Each one of them corresponds to some reaction rule in the RMG database, and RMG can write this down, no trouble. And none of these rates depend on pressure if this collision rate is very fast. And so then everything will be approximately Arrhenius, and everything's great. And this is all like you already learned a long time ago, and you know all about this. And everything works fine. But if I lower the pressure, what happens is that a lot of these energized molecules of C, it might be faster for them to react forwards to form D than it would be for them to get cooled down by collisions, because the pressure of the gas is too low. So I don't have enough collisions to cool them down. So these hot guys are living there, and they're way above the barrier forming D, so they might form D. Some of these guys are also, they're above the barrier to go back to A plus B, so some of them might fall apart also. So you get all those kinds of effects happening. And in fact, if they form D, some of these guys are still above the barrier to form E plus F, so they might even go on to form E plus F. Now, from the macroscopic observation, you don't see these transient species. Okay, so these guys are living so short, it's like short compared to one collision in the gas phase. It's a very short time, even at low pressure. And so this guy's maybe living a microsecond or a couple nanoseconds. So you won't see it. So all you'll see is A plus B disappear, and like E plus F appear. And so now we have all the reactions we had before. A plus B goes to C, C goes to D, D goes to E plus F. But now we get 3 additional reactions. A plus B goes to D, A plus B goes to E plus F, C goes to E plus F. Yeah?
So the C, what's the structure of C star look like? So it's like some close to the vibration state of like a C?
It's a vibrational state of C. So it's C that has a lot of vibrational energy. A lot of times the molecules of C are pretty big that we study. Maybe they have 30, 40 vibrations in them. And on average, you look at C star, it might have like 1 or 2 quanta in each vibrational mode. So it's just a vibrating molecule. It looks like the regular molecule is vibrating a bit. However, there's a process called intramolecular vibrational energy redistribution, where the vibrational energy in one mode can stop vibrating and instead make this one vibrate twice as hard. And that kind of thing going on, and by random chance, sometimes that puts a whole lot of the energy into one bond to the bond membrane. Or it might vibrate 2 pieces together and make 2 atoms hit each other and make a new bond. And so that's what C is doing. So if you look at C star at a given time, it just looks like a normal C, except it looks like the hot bands. If you look in the vibrational spectra, it's like it's looks very similar, except it's not V equals 0. It's like a lot of the vibrations are V equals 1 or V equals 2. But cumulatively, all the energy of all those vibrations adds up to be more than the reaction barrier. And that's because the molecules are relatively big, so it has enough energy to do that. All right, so in this situation, these rate coefficients, like A plus B goes to E plus F, you write it down, it looks like it's a bimolecular reaction. However, there won't be any RMG family that corresponds to this step. But it's a real reaction. It's like a composition of 3 steps, this one, this one, this one, that gives this overall rate. Its rate expression is to be really weird because it has to have a very strong pressure dependence, because as the pressure increases, these intermediates are going to be intercepted by getting cooled down and trapped as the wells, and you won't make E plus F anymore. So you have a very strong pressure dependence on this step, for example. And it also turns out to have a quite non-homogeneous T dependence. Yeah?
So you're basically saying that you don't have C and D, but there's a lot of pressure dependence on E plus B to E plus F, right?
These ones also have pressure dependence too. So as the pressure increases, the A plus B goes to C will be faster, because more of it will get, it'll go back to being like this case. At high pressure, it's all going to C. So basically, everything comes in goes to C, but in this case, only a little bit goes to C. So it looks like the rate coefficient for A plus B to C got slower as we lowered the pressure, and that effect called fall off. It's like the rate coefficients like sort of fall off. Stop being as fast as they used to be as you lower the pressure, which is slightly bizarre, but that's what's going on. Now, how do you solve this? The way you do it is you now have to. You can't think of C as just one species. You have to think about C of different energy levels actually having different rates and being able to do different things. And then you can do energy balances, population balances on the population of each different energy level of C. And if you write down those system of population balances on each level, and you say that all these high energy states are pseudo steady state, so they're high energy, they have very, very small concentrations, and so you can make the quasi steady state approximation for them. And so then you say basically as much stuff is coming in as going out. There's no real accumulation here. And it says this stuff's going this way or it's going this way, and the ratio of which way it goes will depend on the competition between collisions, which are represented in this thing omega here, and rates for the reactions, the rate for the reaction back. All right. And that set of equations gives you a way that if you suppose had a steady state of like A and B coming into the system and reacting, you'd have a steady flow of stuff from A and B coming in, and then some of this is coming back, some is going here, some is going over there, and you can calculate the ratios of where the flow is going by dissolving this system of steady states. And some of these levels are getting like relaxed to this level, which also can react forward with a different rate. And so you can have all the couplings between them, of how they're all getting all relaxed to each other. Okay. So anyway, so you can solve this for sure, and you can get some like rate of formation of D plus E. And usually what's assumed is that D plus E, if you form some products, these guys separate, and we'll just assume that they go off and do something else, like they do react somewhere else or something, and they're out of the picture. So this is like an irreversible sink, the normal Wade's model. All right. And so you can get and that's sort of maybe true in the limit of there's no D plus E concentration 0. You have some A and B. This sort of gives you the forward rate. You could do the thing in reverse, put a lot of D plus E in and see how it would go back to D plus B. Then the other problem, you have this solution where all these energy levels have their own little kinetics about what they're doing. And you can actually observe this experimentally. So it's pretty famous. You do reactions like in the atmosphere. There's reactions like two ozone molecules come together and they make three O2 molecules. That the O2 that's formed is formed highly vibrationally excited up in the stratosphere. And then it has collisions with the gases up there and gradually cools down and forms a Boltzmann distribution. Now, in the stratosphere, the temperature is super low. So the bath gas temperature is super low. But when the O2 is formed, it's formed at like V equals 16 or something like that. It's some outrageously high energy. And it takes it like microseconds to get cooled down. And so you can actually observe spectroscopically and see this highly excited vibration of oxygen. And that has enough energy, like if it bumps into a chlorine or something, it can like react with it. Whereas cold O2, V equals 0, doesn't really have enough energy to do much at that temperature, so it doesn't do much. So you actually have a different reactivity of each of these energy levels, and that's what this K depends on energy. Right, and it's obvious, right? I mean, if you had an energy level here, it's below the barrier, the rate's gonna be really tiny. And here, the rate's gonna be fast, because it's way above the barrier. So, of course, it depends on energy. But because of that, there's different levels. If you could observe them, they all actually behave slightly differently from each other. Now, normally we don't worry about it because we assume we have Boltzmann averaging. So all the vibrational levels have collisions that interchange their energy. And so I just talk about having a molecule of benzene. I don't worry about the fact that I look at one molecule, now it has 0.1 eV of vibrational energy, and I look at it 3 seconds later, it's got 0.13 eV of vibrational energy, and then I look a little bit later, it has 0.05 EVs of vibrational energy. I don't care, right? It's all benzene, right? I don't care exactly how much vibrational energy it has in it. Yeah?
So the example you gave, like two ozone molecules come and collide and make like three O2 molecules.
Yeah.
So ozone is in a single state, collide and make singlet oxygen. So they are so we need to consider the singlet oxygen vibrations.
Yeah, in that case, you also have to worry about the singlet. Yeah, and I don't even know. I don't know about I don't know his own story well enough to tell you. But yeah, and there's a similar one. You have O atoms with O3, and they make two O2s, and I can't remember. One was single, one was triplet. I'm not sure. Anyway, so that's another part of the story is electronic excitation, and then you also have vibrational excitation. This talk will just worry about the vibrational part. Usually, we would treat different electronic states as different species. So sometimes internal conversion and intersystem crossing is so fast, we should treat them all as one. That's another whole topic. All right, so if you're going to try to calculate these rates, the K of T and P, what do you need to know? There's two really important things. One is you have to know what's called the density of states, which is how many quantum states are in each energy interval. These things are something like the free energy or the entropy in the microcanonical point of view. So the density of states, if you do a Boltzmann average or Boltzmann evaluation of this thing, this is the thing which we call the partition function Q. So this is the Helmholtz free energy of the molecule is related to this density thing. This is like the Laplace transform of density gives you the Helmholtz free energy. But this is quite important back here. So for example, you have this kind of thing where it's going back and forth. And in how much it wants to be on this side and how much it wants to be on this side sort of depends on how many quantum states are here. So I just drew one, but actually there's a whole ton of quantum states right in there. And the one that has the most quantum states will be where the sort of equilibrium would lie. So that's a very important number for this. And it's related to the vibrational frequencies of the molecules. That's what the rho of is related to. The other one is the microcanonical rate coefficient, K of E. So this is the thing, if you Boltzmann average it, you'll get the K of T that we're familiar with. Okay? So if it was Boltzmann, then they would just have this nice relationship like that and everything would be great. But if we don't have a Boltzmann distribution, during the time we're doing this reaction. So this is not really the right weighting factor to use for during the steady state. But if you wait a long time, let everything get to equilibrium, that would be the right factor, because everything would be thermal again. If you want to compute the K of E and the rho of E, you can compute them from the vibrational frequencies and the geometries of the molecule and of the transition state. So for the rho of E, you just need the molecule. For the K of E, you also need the transition state properties. So if you do a quantum chemistry calculation, it's perfectly straightforward to compute these things. I say perfectly straightforward, it's actually still slightly subtle to do it right, but there's formulas you can just plug it in. If you get the right formula and you plug it in correctly, you'll get the right answer. Though I've seen people screw this up too, for sure. And so if you have the quantum, that's the way to do it. If you don't have the quantum, you can estimate this by doing what's called an inverse Laplace transform. Since these things are like Laplace transforms, like Q is the Laplace transform of rho, Q times K is the Laplace transform of rho of K. Then you can do inverse Laplace transforms to figure these things out. However, inverse Laplace transforms have a lot of bad mathematical properties. So the real rho of E is actually pretty jaggedy. It's not very smooth. But the methods we have for doing the inverse Laplace transform assume everything's smooth. So that's one problem. Another problem is that even for smooth functions, you need to have all the information from 0 to infinity in order to do the inverse Laplace transform. But typically we don't really know these things at all temperatures from 0 to infinity. We usually only know them from like room temperature to 1500 Kelvin or something. And so we have to like guess what's happening below room temperature, and we have to guess what's happening at high temperature. And if we make bad guesses, that actually affects our calculation of the K of E and the rho of E. So this is you can definitely do it, but numerically it's not that accurate. So it's one of the reasons we're having trouble with this. Yeah.
So in the previous picture you showed that AB going to C, looks like a varyless reaction, so
Yeah.
there won't be T's. So then how can someone get the density of states in that case?
You can do the density of states is really just a property of the molecules. It's like how many energy levels are here. Here it's A and B. I would treat them as two separate molecules and just do a convolution of all the energy quantum states you could make with the two of them, where the total energy sums up to E. Actually doing it is a little complicated, but in principle it's not that hard. If you have it's just enumerating all the quantum states that exist and figure how many of them fall into a certain energy interval, and then the number of those quantum states divided by the energy interval width is the rho. And there's some algorithms how to do that if you know all the properties for the energy levels, which is the vibrational frequencies and the geometry. Now you might have some rotors, and it might make it a little complicated, and there's some rotational things that makes it a little complicated. So there's a lot of complications, but in principle, it's like not impossible to do it, and it's really just a property of the molecule, the rho. The K of E, you need to have a rate expression. If you have a barrier, it's straightforward to do it. If you don't have a barrier, you have to use like variational transition state theory to get it. And there's nice papers by Klippenstein that show recipes of how to do that. Again, we have the recipe, it looks straightforward. If you actually try to do it, it's actually sort of complicated. And different ways of doing it might give you slightly different answers. So. But in principle, you can do it. Stephen Klippenstein can do it. All right. Now, a practical thing, the one issue is like, can we calculate this stuff? Another one is, can RMG handle it? So, problem for RMG is the fact that we can now jump like from A plus B to E plus F. This is like totally different than what RMG was doing before, because we're doing core edge, where we're assuming that the edge was connected to the core by a single step. But now, what is a single step if I can jump 3 steps at one time? So this leads to a lot of complications in the algorithm. And to do this, what RMG does is it actually does a single step to a C star and treats these like a sequential thing and keeps track of this whole network and then uses that to build the whole network, and then it goes back to that program that would compute the K of TPs for the whole network together. But it's a lot of bookkeeping. And again, this is like, it's possible to do it. There's papers papers in the literature explain how to do it. Many of the papers from my group, but also by other people. Not that many people can do it that well. And RMG, I think, is still the only program that can do it automatically. It's kind of complicated. And there was 2 whole PhD theses of students in the group to do this. So it was quite a lot of bookkeeping. And some of you may end up having to delve into that part of RMG to work on it. I think they wrote pretty good papers and theses and probably can figure it out, but it's definitely not a trivial coding thing. However, on the other point of view, it's a really fantastic thing about RMG that you can do this. In the past, all these calculations were just done by hand, where humans had to write down and think about all the different possible steps and do it all. And that's really, really painful to do. Whereas RMG, you'll see, you can calculate 100 of these things in 10 seconds and press go. And it'll tell you all these rate constants. Whereas if you're doing it by hand, it might be each one might be a 3-week process for you to do it. All right, so let's talk roughly how RMG works. So RMG starts by identifying A plus B can react, and it sees that it makes a unimolecular product. So it's in the family that makes unimolecular products. It's one of the, they're separated into different families. And it says, oh, if it's unimolecular, therefore, it could form C excited. So at this moment, it says, okay, this reaction is fast enough. I want to put it into the model, but I'm worried because I know if PDEP is on, that this might actually just be the energized form, and it's not really the species I want, which is this one down here maybe. So instead, it starts a new PDEP network, and it explores what C star can do. So it always puts in that C star could get relaxed, and then it tries to see what reactions in one step you could do from C star over one barrier. And so it might find maybe from D. So now, at this moment, it has A plus B plus C star. It always puts C in. And the question is it going to add D or not? Is D important enough? And this is the same kind of decision that RMG has to make all the time, when it decides whether or not an edge species is important enough to put in. So we have to be able to figure out how to evaluate kind of this flux to see if how high that is compared to the tolerance fluxes we have, like tau move to core. So yeah.
Do you enter further from D star to Z?
You'll keep going.
Keep going until it's
Yeah. If you can understand this one, you'll be able to understand the rest of them. Yeah. Just like RMG normally just teach iteratively adding stuff, right? It's the same kind of thing. Oh, that's interesting. All right, so in so on the RMG website, there's some really excellent documentation that you should definitely read. And one part is all about this pressure-dependent stuff. And so it talks about how it identifies the stars, the species that are like the energized transient intermediates. And then it has this very interesting plot. This is like, when do I need to worry about this? And this is by a former student in the group named Brian Wong. And he did an analysis for just a couple reactions where he changed the size of the molecule, changed the temperature, changed the pressure, and said, how close is the rate that you get after you do all this analysis from the high pressure limit rate? And if the temperature is low and the pressure is high, so you're up in this quadrant, then the high pressure limit rate and the rate you do from this whole complicated calculation turn out to be about the same. And so you don't need to bother with it. So basically stuff up here, you don't have to worry about it. So for this type of reaction he was doing, you're in the range of like, below 800 Kelvin and above an atmosphere, you really don't have to worry about this stuff. And on the other hand, if you're at 1500 Kelvin, even in an atmosphere, even for gigantic molecules, you still have to worry about the pressure dependence. So if you're doing combustion problems, you always have to worry about the pressure dependence. And in fact, almost every reaction that can form unimolecular is going to be pressure dependent significantly. If you're doing atmospheric chemistry problems, almost everything is pressure independent because you're down at 300 Kelvin, way down here. Yeah.
Like how accurate like pressure range is very long, like 100 bar range if you do it, and then only one bar we are focusing in. So these rate coefficients that like how accurate when compared to long range pressure.
So as you go up in the pressure, once you're above these lines, you're pressure independent. You're in the high pressure limit, which means the Boltzmann thermalization process is fast compared to your reactions. So lots and lots of reactions at low temperature, above an atmospheric pressure, you don't need to worry about it. If you're somewhere like 1,000 Kelvin, like actually the Ghent group works a lot in the pyrolysis stuff, it's a little bit unclear. So they're usually working a little bit above atmospheric pressure, and it's like the small molecule reactions will be pressure dependent, and the large molecule reactions are not. They're right in the border, and you have to kind of check. But also it means that the scale of the effect won't be that big. So it might be factors of 2 and 3. It's not like factors of 100. When you get up to here, it's gigantic. So the pressure dependent effect can be many orders of magnitude. And you may make completely different products than what you would expect from the high pressure case. So it's really to worry about. Yeah.
So is it within the, I guess, the band, so to speak, of that plot where the pressure dependence are kind of in the fall off regime? And then like either side, above or below, it's either high pressure or low
This
pressure?
band is for different size molecules. So the density of states increases very rapidly with the size of the molecule. And if the density of states is really high, the molecule sort of acts like its own internal thermal bath. And so when you have a lot of, this is like the number of vibrational modes. You have a huge molecule, it's 1,000 vibrational modes. It sort of acts like its own thermal bath, and even down to, 1 torr pressures, you might not need to worry about pressure dependence. But for small molecules, they're like this blue or green lines, then a lot of things are pressure dependent because you don't have very much density of states. You don't, how do I explain this? The thing can't live as the energized thing very long because there's not very many quantum states for like the energy to hide in, and so it's going to quickly find a way out if it's above the barrier. If the molecule has a lot of degrees of freedom, you might have 1,000 vibrations. You need to get 50 of those quanta into one mode, say, to break the bond. It's like pretty unlikely that by random chance you're going to end up over there. So that's means it's going to live a long time before the reaction happens, which gives plenty of time for collisional energy transfer with the bath. So the big molecules are not as affected. But this effect is kind of small. So this is like, maybe 1 or 2 orders of magnitude in pressure worth. Also, the strong T dependence is super important. So this is more important than the pressure, actually. Is that the small changes in temperature can really move where you are in this diagram a lot. All right. And you already read this paper, there it is. You're going to go look in the documentation. And explain exactly what this plot is. All right, let's go back to here. All right. All right, so you want to know whether D was important. So we need an edge flux to test if RD is greater than tolerance move to core, whatever our tolerance is going to be, times some characteristic rate. And it's going to be some pressure dependent rate coefficient times the concentration of A from A to D, or concentration of A to B. In the case I showed you, A plus B goes to the intermediate, goes to D. So I wanted the overall rate through these 2 transition states to get to D. However, to compute this, I'd have to know the whole story. But I don't have it yet because I haven't even figured out what D would do yet, so I can't really solve the whole thing. So instead what I do is I use an upper bound on this rate coefficient to get an overestimate of how important this is. And then if that overestimate is still less than the tolerance, then I can say I don't need to worry about it, and D is unimportant. So RMG tries to build overestimates of the steps that it doesn't know about yet. And then it can do this evaluation. And there's a whole thing about how to do the overestimates correctly and stuff, which is another,
From your previous sheet, if you were to go A plus B to E and F, you first have to evaluate if D is important,
Yeah.
and then go further to E and
Yeah.
F, because D might also be like in a vibrational state and not.
Yeah. Your D will be a vibrational state, yeah. So the thing is, so what I'm trying to decide is when I come in with A plus B, I have a certain amount of flux, and some of it's going to go down to C and some of it's going to go to D. And if I'm at a condition where I use an overestimate of D, and I still get that the total amount going this way is really small, then I can know that I'm not going to get much E plus F either, because all the E plus F has to come through D.
So the overestimate is not for B, but for D star.
Yeah, pretty certain. Yeah. All right. So suppose it does this evaluation and decides that D star actually could be formed at a high rate. Then I have to put D star in. So then it'll add D, and then it'll try to see what D star can do, and it might find that D star could form E plus F. And then we'll do the same process again, where now it makes an overestimate of the rate from D star to E plus F, and then evaluates whether E plus F can be formed. Yeah?
So in the RMG, let's say I make a thermal entry with quantum calculation, I have C, I have D, E, I calculate everything. But in the thermal entry itself, I'm not giving the vibration frequency. Can we add that to like the library itself so we can easily calculate these?
Yeah, so right now we don't have that in RMG, but it would be really smart to add it. But we don't have it. So right now, if you use RMG, it will try to make an estimate of the vibrational frequencies needed to do this calculation, which introduces another level of error in the calculation. So if you actually had the real numbers, you could do much better. With Arcane, you could just put in the real numbers and get a much better number for this rate constant. But the disadvantage is then you have to sort of do it by hand and load it up correctly and everything. And the RMG one's so nice, you just press go, and it just discovered this reaction exists and do the whole thing. But it's making decisions based on slightly sloppy numbers. And so it may not be 100% reliable about what RMG decides to do. It works well enough that we're publishing papers and modeling systems, so it's not terrible, but it's like, you can definitely find cases where it's like, off by order of magnitude in its predictions or something, one of these steps. And so if that turns out to be crucial, so if this rate is really tiny, RMG will get it right, and you don't have to bother. But if this thing is kind of close to the tolerance, it's definitely possible RMG might get it wrong, and it should have been in the model, but RMG mistakenly left it out. Yeah.
When RMG finds these in the model, are they usually kind of small, isolated networks, or are they interconnected and spanning the whole thing?
They get pretty big. If you have big molecules in your system, they can do a lot of different reactions. You get many of these things, and particularly ones that, if you have a radical, often there'll be like a dozen radicals that all have kind of comparable energies. So there'll be a lot of these intermediate wells. So instead of just having 2 of these, you might have 24 of these guys, all with different barriers and different depths. And exactly which ones are important might depend like which channel you came in from, with how much energy. And this could be like a total nightmare how to do this. And I think currently in RMG, it sort of keeps track of where it came in from, and it computes the network that you would get from A plus B. Later you might form E plus F and come in this way, and this comes in at a lower energy than this, so its decisions about what's connected to what might be different. And that's like another whole headache. And maybe in principle we should put them all together, but then that's a programming thing of how to tie them together properly. So anyway, that's the way there's a certain way it's coded right now that works, but I would not certify it's the very best way you could possibly do it. Yeah.
So kind of the follow on from that, since that's a complicated problem, it seems like it's not straightforward to, say, use RMG to identify the pressure-dependent system inside the model, and then take it back out to Arcane, do a better calculation, and then like seed that in. That seems
I think that you could definitely would be possible to do that. I don't think that that's coded right now.
Like on the fly, sorry?
Like if,
No, like run a sensitivity analysis. If you're sensitive to a pressure-dependent rate,
once you identify
calculate.
where these networks are,
Yeah,
go
you
back
can
to
get the whole network.
Arcane, and then do like, say, a training reaction with the pressure-dependent systems, where you're like, I did this in Arcane, use these rates, these are better.
when you say go to Arcane, you need quantum calculations, right?
Yeah.
Which are in RMG estimates.
Yep, I'm saying,
Yeah, so,
I'm saying
like, go
outside
do
of
the
RMG,
entire- Yeah.
leave RMG, you in your own time take a week and do this,
Yeah.
and then come back and
So
seed it.
I think it's definitely possible for you to get it to spit out that it had this network.
It's already in the output.
It's already in the output.
automatically-
It's there.
The PDEF folder has a list of all networks.
Yeah.
You have to figure out what the index is, but
Yeah. So, but making a convenient tool to go from that output to what you just said, we don't have it right now, but that would definitely be a feasible thing to do. Particularly if ARC was able to do the transition states correctly, then that would be not so hard to do. But nobody's done it yet, so it's be a nice possible thing to do.
isn't it quite, I mean, because the files, the outputs are arcane readable.
Right, but you still have to have the guesses of the geometries, right?
Oh, well, yes,
Yeah,
of course
yeah.
we have to do the whole quantum calculation
Yeah.
thing, but I feel like we're
We're almost there.
short of mixing in like more arc with all of this. I feel like we're giving you the network in the format for arcane already. I mean,
Yeah, so right now for the human, to be a little bit of file moving, but I think that's trivial actually. The hard part would be you'd have to go through, and there might be 27 barriers, and you'd have to give initial guesses for all of them and get the quantum calculations to convert for all 27. But then otherwise, I think Arcane would take the rest of the way. And then you could feed it back into RMG as a library for this reaction, and I think that would work okay. Yeah.
If I use that for my RMG model,
Yep.
I get the whole mechanism. But the rate in the output file, is it high pressure?
No, if you turn PDEP on, the rate that comes out is probably a Chebyshev polynomial. So it's a form that has a P dependence in it.
Oh, and then other solvers can.
Some other solvers, like ChemKin Pro, can read it, and maybe Cantera. So there's some solvers that can read the Chebyshev format and solve it for you. Some of the solvers cannot.
When you have a PDEF on the RMG, and let's say you have like a low temperature and high temperature region, based on the plot you showed before, the low temperature region, because you don't have the pressure dependence, is it gonna like automatically get turned off?
No, the human sets, if you want PDEP to be a 1 or not, if RNG might assess that this particular reactions, PDEP reactions are not important, and then it would just find what would be the normal high pressure limit ones. But if you said, please run with PDEP 1 in the option deck when you run RMG, it will try to do PDEP for every reaction. And then it might numerically establish which ones it thinks are really PDEP or not.
Or you can set a maximum number of atoms that below or above which it will do PDEF work.
Okay, yeah. All right. So we did this already. All right, and the whole algorithm, the way this works conceptually, is the same as the core edge algorithm. It's just more complicated because you have to keep track of where you came in from for each one separately. It's more bookkeeping, but basically not such a big deal. All right. Notation in the files. If you write in a case, say, a ChemKin file, A plus B goes to E plus F, it's going to read that as a high P limit rate, and it's going to say it's near Arrhenius. And it's going to expect Arrhenius parameters to come in, A, N, and EA. If you write with the parentheses plus M, then it's going to expect it to be PDEP. And so it might expect it to be a Chebyshev or other forms, other forms, log P form. And the way it's going to evaluate the rate is it's going to get the PDEP expression, evaluate it, and then multiply it by the concentration of A, concentration of B. It's not going to include the concentration of M in that rate law. If you write it this way, A plus B plus M equals E plus F plus M, that's going to assume you're in the extreme low pressure limit, and it's going to actually evaluate its concentration of A, concentration of B, concentration of M. Notice that K now has different units because of one more factor of inverse concentration in there. Okay, so here's the plot I showed before. So there's normal chemistry, there's laboratory flame chemistry, and you can see that this is the very pressure dependent, this is pressure independent, high pressure limit. History. So this stuff was invented by me and my first student, David Matthew. And at that time, David implemented it into, Exxon had a program called NetGen, which we renamed XMG PDEP after he added the PDEP stuff to it. This was before RMG was even invented. Then RMG was created but there was some copyright problem with Exxon, and we couldn't use the PDEP stuff in the RMG software. So the original RMG, which is now called RMG Java, didn't have PDEP in it. But the algorithms are mostly all worked out by David Matthew, and there's a couple really nice papers by David Matthew about that. Then a little bit later, David and Brian Wong figured out that assessment of when PDEP is necessary or not. Then maybe 8 years later, there was a student named Josh Allen, and he created RMG Pi with inspiration from Richard West, with some good interactions with Connie and Franklin, and it was basically a rewrite of RMG Java and RMG Pi, but at the same time he also added all the PDEP stuff, which he recoded himself since we did not have access to he couldn't go from the XMD PDEP because of the copyright problem. And at that time he wrote the original version of, it was called Cantherm, which was now called Arcane. Confusingly, there was another program called Cantherm, written by Sandeep Sharma, that did not include PDEP. So the literature about this is very confused because he used the same name for the two different programs. And then now all of this is getting rationalized into Arcane. So David and Josh's PhD thesis have big discussions about a lot of details of these calculations. And then this one paper by Josh with Franklin is a really good paper showing a lot of technical details of how the calculations are done and different options and what they're doing and what they affect, how much they affect the accuracy. All right, this is just for you. You can look up. There's two different sets of classes in RMG that have to do with this. The coding is not as transparent and clear as it should be, but that's the way it is. Now the master equations, if you just solve them as a time-dependent problem, you would get the population of each energy state as a function of time. That is not a rate coefficient. This is a time-dependent population. This is a rate coefficient is like units and stuff. It's like completely different. And typically there's thousands of energy states, but there's only a few molecules in the network. And then the time dependencies of these guys, each of them is a sum of typically thousands of exponentials. So they're like the relationship between those things and the rate coefficients is like not obvious at all. And what you really want to do in practice is you want to lump all the vibrational states of some molecule and basically say that's all the same molecule. I don't care what vibrational state it is, because eventually it's going to be Boltzmanns anyway. So I just want to know like how much benzene is coming out of this reaction. And I don't care if it's V equals 17 or V equals 2, it's still benzene. So I want to put them all together and then somehow get an effective rate constant that's the overall rate constant leading to benzene. That's my goal. There's different methods how to do this, and they give different rates. So this is like a huge confusion in the literature about this topic. There's 3 methods are implemented in RMG. The one that's used in RMG is really the modified strong collision approximation. And Josh has a nice discussion about it in that paper with BCCP. And this one is by far the most robust and simple, numerically fast. So for RMG, if you just want a rough number, this is a really great way to go. However, it's pretty rough. And so if you really wanted the accurate number, this is not really the way to go. This method, the chemically significant eigenvalues method, I think this is considered to be the best method currently available. Still not perfect, but it's a pretty good method. And Klippstein and Miller wrote several really nice papers about this. It was actually invented before by a guy named Whittam a long time ago, but he just wrote one paper on it, wasn't noticed. And then he moved on to different areas, and then these guys picked it up. Well, they rediscovered it later. And there's this other paper that's also in RMG called the Reservoir States Method. I recommend don't use this method unless you really know what you're doing, because it has a lot of different ways it can fail. They all turn out to be written in the same mathematical format. You can look at this link to see it, and Josh's paper has more discussion about that, but I think I'm not going to do that because of time. But let me just say what the modified strong collision is, because that's what you probably use the most, is that the assumption is that a single collision is sufficient to take your energized molecule and cool it all the way down to become the Boltzmannized C molecule. And this is a huge simplification of the math because it ignores all the collisional stuff where in reality the molecules are getting knocked down, then knocked up, then knocked down, then knocked up. It's like diffusing in energy space because any molecule can do anything. And so you get all this kind of coupling between the different levels. But if you assume that each one only connects all the way down to Boltzmann-ized stuff, then you just jump over all that and then it decouples all the energy levels from each other. And it also removes all of the excited states that can't react, that are below the barriers, are basically out of this problem. So that makes it really simple too. And so this takes that master equation, which is a gigantic system of thousands, a couple differential equations, to just a couple independent small linear algebra problems. It's pretty rough. And so the two cases we've done the test, it introduces errors of about a factor of 3 in the minor product channels. Usually it's a major product channel, pretty close to true, but the minor ones can be pretty far off. However, our rho of e's and our k of e's coming from inverse Laplace transform also have errors that can be more than factors of 3 anyway. So this extra factor of 3 is not that much of a big deal. But it really should also help you remember RMG is not telling you the truth. It's RMG's trying to give you estimates, but they could easily be off by factor 10 just because of this kind of stuff, just in the pressure dependence. Not to mention if your barrier number was wrong, your thermal number was wrong or something, which could also give you pretty big errors. But if you're in a very rough world, this is fine. It's definitely good to separate fast from slow, but if it's medium, you don't know.
Is that all collision? So like, if it's, maybe if we consider connecting the organic, that's enough to rule it out?
Actually, what they usually do is scale by a factor of 1/10 or something. So they take the collision rate and they divide it by some number that's recommended in the literature, and that's like, so it's either the collision does nothing, or it completely cools it. That's the assumption, really. And somebody did a case with a single well and derived this parameter of what fraction of the collisions take it all the way down, and that works for that case. And then we just use it for these multi-well cases, even though no one knows if it's really the true formula or not. There's some papers by Troa about that topic. The CSE method instead does like an eigenvalue analysis of this giant matrix equation, and then there's a clever linear algebra trick that you can use to construct what the K should be. And so if you have really great K of E's and rho of E's from quantum that you really believe are really great, you definitely should use the CSE method. So if you're doing it by hand in Arcane, I would recommend you always use CSE as your first try, because you preserve your accuracy. You're not going to introduce another factor of 3 error by the method. However, it requires solving a very large matrix eigenvalue problem, and so it can be slow. The computer might not be able to handle the matrices. If the matrix is super stiff, sometimes it'll fail, which happens often at low temperature, so low temperatures usually fails. At high temperature, there's a physical problem, all the methods actually have, is that some of the equilibria, for example, in this case, suppose this barrier was even lower, like down here. Then you might have a lot of situations where C and D are actually fast equilibrium with each other all the time, at all the range conditions you care about. In which case, it's silly to treat them as C and D as two separate species. They should just be one species, so they're always in equilibrium. So in that case, the CSE method fails. It has a numerical problem. But really, it's not a numerical problem. It's really a physical problem. That really these are one species, so they should not be treated as two separate species anyway. Georgieski has written some algorithm to identify when this happens and then replace C and D by one species, CD. That's the two of them together, and then it works fine for that case. We don't have that implemented right now. We should probably. All right, let's not bother with that one. Technical issues. We have a lot of technical issues about how we calculate the KVs and the rho of E's. I don't believe them that perfectly at all. And this is a very important issue. Actually, if you want to prove accuracy of RMG, it'd be better ways to do this. However, it works all the time. It's fast.
Can you give like a ballpark on what you consider as a high T and low T, like about 1,000 KV? What are the
For me, most cases I've seen, if you're below 800K, you usually don't have to worry about pressure dependence. Okay? Sometimes if you go to very low, like in our lab, sometimes we go down to 10 torr or 5 torr or something, then you'll see, even a little bit below 800K, you'll see some pressure dependence. But somewhere around there is where it poops out. in all the kind of normal pressures I've ever seen. Yeah, and the same in high pressure, maybe above 100 bar, you never need to worry about pressure dependence no matter what the temperature is. Yeah.
So when you say you don't have to worry about pressure dependent, if you look at the initial delay, let's say for an oxidation reaction,
Yeah.
and you're seeing that it doesn't matter, then you look at the modified Arrhenius parameters, there usually is like a P to like a beta term there. So does that term go to 0 in the low, like below 800 Kelvin?
So I'm sorry, so this is the fit to the ignition delay, or is this the mechanism?
The fit to the initial delay.
Yeah, so definitely the ignition delay depends on pressure, but the biggest part of that is the concentration effects. The concentration effects of the bimolecular reactions. So that's always present, and you can't avoid worrying about that. But this K, whether the K separately also depends on pressure, is more specialized, and it's mostly for high temperature and moderate or low pressures. All right. I don't know if this is still true. Are they exactly the same or not? No. It's still not exactly the same. They're pretty darn close, but I think there's some classes that are not exactly used for both of them. So they're not exactly the same, which actually means if you do modify this, you need to pay attention to what you're doing because you could make them incompatible with each other or something. And
There's subtle differences.
the subtle things are not quite right. Some of the RMG tools do not work well if the PDEP is on. For example, I think pruning does not work inside PDEP, at least not inside the network. And there's some numerical parameters in the solution, and it does something semi-reasonable to try to get a good solution, but I don't think this is 100% robust, and occasionally we'll have errors where something went wrong with this numerical stuff. And also, the discretized values using the PDEP calculation are definitely not consistent with the thermo because they're derived from this inverse Laplace thing, which is approximate. So we're using like approximate thermo. And so sometimes you'll see some weird discrepancies because the macrothermo and this microthermo are not exactly the same numbers. It's a little bit subtle, and unless you look carefully, you won't notice it, but it's definitely, there's something there. And that's all I got about PDEP. All right. Next, do we have an exercise?
Yeah, so we'll be discussing arcane. I think maybe the audience would like some break, right? So we can take a 10-minute break.
Okay.